suppose you have replicated data. An example, possible example might be go back to the school, or think of, suppose that we categorize the firms that we have sampled into different size classes. Small firms, medium, small cap, mid cap, and large cap firms. How's that? Those are some finance words that I know. I don't know many, but that's three. And that's 3 out of the list of 10. So small cap, 4. Small cap, mid cap, and large cap funds. Okay. So those are the 3 size classes. And I can collect a bunch of firms that are members of the small cap group. I can collect data on a bunch of firms that are members of the mid cap group. And similarly for the large cap group. And I think that the disturbance term for small firms is homoscedastic. And I think that the disturbance for mid-cap firms is different from small, but homoscedastic in that class. And for large-cap firms, I think that the error variance matrix is homoscedastic, but different from the other two. So now I have a replicated sample. And so how do I test for heteroscedasticity in replicated data? Well, when I have that circumstance, the example that I just gave you with my 3 capitalization sizes, I had small, medium, and large capitalizations. I have a bunch of observations in the small cap group, and I have a bunch of observations in the mid cap group, and another set of observations in the large cap group. So in the group of small firms, I have some error variance times an identity matrix, whose dimension is the number of firms in that class. For the medium size, I have another error variance times an identity matrix of that size, the number of firms in that class, and the same down here for the big firms. So under the null hypothesis, the variance in each size class, or variance, is the same as I compare the different size classes. So that would be my null hypothesis, and I want to test to see whether or not the null hypothesis is false. And so I specify the null hypothesis as the variance in the small firms is the same as the variance in the medium firms is the same as the variance for the big firms. So how do I construct a test statistic for this null hypothesis? We'll pool the data, presume that the intercepts and the slopes are the same across the size classes, and we'll estimate our regression coefficients, and we'll take those residual sums of squares, and we'll construct a sigma hat squared, which uses all the least squares errors as though the errors were homoscedastic across the size classes. So that's my E transpose E over the sum of the NI, where NI is the number of firms in a given size class. And then, using the same set of regression coefficients, slopes and intercepts, which I presume to be the same across the different size classes, I construct a new set of squared errors within the ith class. And I construct a sigma I squared hat. So in my 3 size class example, I would take the estimated regression coefficients, compute the residuals within that class, calculate the sum of squared errors, divide by the number of firms in that class, and I'd have a sigma hat squared sub I. The index identifies the size class. And then the test statistic actually is a maximum likelihood test statistic. If the error terms are jointly normally distributed, under the null hypothesis, the part that's up in the exponent of the normal density function, which is the only important part, the log likelihood, the important part of the log likelihood, is just log of sigma hat squared from the top line. And you're comparing that log likelihood to the alternate hypothesis, where the error variances are different between the different size classes. And that has a chi-square distribution. We already know that from what we were talking about when we talked about likelihood ratio tests. So this is a particular form of a likelihood you reject, this is supposed to be a wiggle, but Bill Gates thwarted my efforts to have nice looking typefaces. So that test statistic has a chi-square distribution, where the degrees of freedom is little m minus 1, where here little m represents the number of size classes that we have. So if we had just had small cap, big cap, large cap, it would be, little m would be 3.
And that's a minus between the two terms, right? Not an equals.
And this is a minus sign.
Okay.
So it's the total size of the sample times the log of sigma hat squared minus the weighted average of the log of the sigma I squares, where the weights are the number of firms in the size class, for example. By the way, at step 3, well actually step 2 and 3, I commented that the slope and intercept were the same for the 3 different size classes, right?
Mm-hmm.
That's a testable proposition in its own right. So again, this is part of the art of the econometrics. We just got finished talking about what to do when we believe that the slope and the intercept may or may not differ across size classes. Why couldn't we implement the 2 procedures? The testable proposition about slopes and intercepts is an independent question from the question about heteroscedasticity. There's nothing that says that we can't entertain both questions in the same study. Then the question only is, in what order should we entertain them? Should we test for equality of slopes and coefficients first, knowing that if we don't correct for heteroscedasticity, our t-tests are going to be, the level of the test, the significance level of the test, is going to be thrown off a little bit? Or should we impose the restriction that slopes and intercepts are the same, knowing that that's going to do some harm to our test for homoscedasticity? Well, you would do both of them, both ways. You could test for slopes and intercepts being equal first, go on and test for heteroscedasticity, then go back and redo. Once you know how to construct the efficient estimator, go back and redo the test for equality of slopes and intercepts, and then redo the test for heteroscedasticity again. So you could iterate back and forth until your test statistics and your coefficients stabilized. That there was no change in them from step to step. All right? So looking at heteroscedasticity doesn't preclude the question of the specification of the right-hand side, and vice versa.